Cool. So now we have lightning talks. First up, please welcome Dr. Maureen Denolle, Assistant Professor of Earth and Space Sciences at the University of Washington.
Good morning, everyone. Let's start sharing. And I'm going to ask the same question every time. Do you see presenter mode?
Yes.
Excellent. Great. Thank you so much. So I'm representing a great team of graduate students and undergrads and collaborators. So this is basically the way we deal with seismology. We look at all of the sensors that are recording vibrations of the ground in the world. And our typical big data workflow, we can have over 100,000 stations, is to query an archive that's actually located in Seattle that has about a petabyte of seismic data, but there's more today in other archives. And we just query and download the data and process it. We have very simple workflows of downloading the data, detrending, demeaning, various time series analysis. And typical workflows is one code and apply it on many files. And so what we're trying to transition our field today is to go from this boring multi-desktop approach of downloading to moving to a cloud infrastructure. It's taking some time to transition. One of the challenges we're facing is we want a really good cloud-friendly data format. And H5, as you probably know, is a little bit of a funky one to have terabytes hosted on the object stores and trying to read it on local instances. So we're working with NASA to use their really smart new H5 core library to read really quickly and efficiently H5 files that are on big archives, but we're adapting it to our standard seismic data format. And JP Zwiski, who's amazing, has done some really cool speed up. And as a young PI, when you pay for compute, you care about faster read times. I'll show you a few examples of what we've been doing. The reason why we're choosing AWS is because there is over 200 or 300 terabytes of seismic data already stored there. So one example of our research is to look at the California-wide network. We've used web services to download data. We've used the S3 bucket of already existing data for various networks. And the things we're developing is, cost analysis and scaling analysis, how many billions of correlations we can do, and how cheaper we can do. So we're still trying to optimize these codes, but preliminary work from a really smart undergraduate student that shows he's done, for $10, done like really massive cross correlations of all of these vibrations that we're recording. And I'm showing here an example of how waves propagate from the source of the sensor and propagate away from, as distance increases, the waves take some time to travel. So we're getting cool physics behind these measurements. Another example from my grad student who's led a lot of the tutorial development for cloud seismology actually is to turn all of these, hundreds of terabytes of seismic data to look at how the near surface Earth is changing through time. So what you can see in the x-axis is time in years, and the y-axis is at different stations located in the Los Angeles area, how the seismic velocity, which are effectively the rheological response of the subsurface, the upper 100 meters of soil, how these are changing with time. And what we're finding is temperature, precipitation, everything changes the mechanical properties of the Earth. And because of drought spells, as we all know, that are leading to these fires, we see actually the velocities are increasing, which means that the materials are getting stiffer as they are drying up over these decadal changes. It's really cool. But that means we have to reassess seismic hazard. Other things we are looking at is end-to-end workflows for earthquake detections. This is not my group, but I'm putting him on the spot. He's great grad student from Stanford who developed the ML-based earthquake detector, where all the modules are machine learning models to pick seismograms, download them, pick seismograms, and output earthquake locations. We're also trying to do web APIs to be more user-friendly because it's quite difficult to teach this material to understand what's under the hood. And then we should have something funded, a great project, hopefully a good cloud bank proposal where we're trying to actually do a hybrid cloud and HPC infrastructure. So we're learning how we can have all of our data flow on the cloud, but benefit from a traditional HPC infrastructure for wave field modeling and things like that. So that's it.
Oh, awesome stuff. Thank you, Maureen. Next up, please welcome Dr. Tyson Swetnam, Research Assistant Professor of Geoinformatics at the University of Arizona.
Okay, can you guys hear me?
Yeah.
Yep. Can you see the screen?
Yep.
Okay, here we go. All right, thank you. I'm here today to talk about cloud native science. So when I use the term cloud native science, I'm trying to describe a functional technique for working in cyber infrastructure where data are progressively migrating up toward living on the cloud. Researchers need to get away from doing work on their laptops, and to develop a research object from the onset of your project until the end is one way to do this. In this framework, the currency of the realm is measured in how we utilize containers to do our research. And we've learned about containers a lot this morning. We want our data to be fair and that the software, analytical code, and the resulting publications are made open source and open access at the end of it. And last, everything we create needs to have an appropriate metadata such that they're machine readable and searchable and therefore findable in the future. So here are 3 common use cases where researchers have come in looking to use CyVerse. On the left is a user who is struggling with getting their data moved onto the cloud or to use data which are already hosted on cloud. In the middle, a user who needs access to cyber infrastructure to get their data analyzed. And on the right, the novice user, someone who has no idea where to go or even where to start. So first, let's look at the central use case, which is scaling up. When I work in the cloud, I want a workbench from which I can orchestrate my analyses. And for CyVerse, we call this workbench the discovery environment, or the DE for short. It's built on Kubernetes and it uses HD Condor. It allows users to start workflows on our resources, or they can spin these out onto other parts of the NSF Exceed. It relies on containers presently focused on Docker, and we're managing a Harbor registry to hold these. We have a 5 petabyte data store right now, which is orchestrated with iRods across a distributed set of nodes in Arizona, and these are mirrored at the Texas Advanced Computing Center every night. And we're using OAuth with CI login and Keycloak to manage the authentication and the authorization of the platform. Recently, the DE added interactive applications, and essentially these are browser-based apps which have graphic user interfaces. So popular research software, including Project Jupyter for Python, RStudio for running R, as well as remote desktop applications running with WebGL that can be run on GPUs. Users bring their own Docker containers, and these can be from either public or private container registries, and they can deploy them as privately owned applications in the discovery environment. On the right, you can see me log into the DE and connect to a running Jupyter lab, which has a notebook. This particular notebook is calling the CyVerse API for launching additional applications or workflows through our HD Condor nodes or back through Kubernetes. And these notebooks are useful because they can be used for exploratory analyses or for teaching. So we're taking what we call a Lego block approach. The name Lego is an abbreviation of 2 Danish words, leg godt, meaning play well. So we want to play well together. By bringing our own tools and integrating them with continuous development approach, researchers can build their own workflows inside of CyVerse. Our team are currently working to enable users to bring their own cloud services. So part of the reason I'm here today. And this will be more public with the release of Jetstream 2 in the beginning of 2022. So our guy on the left, what about our users who can't get his data uploaded? Data downloads are bottlenecked by network speed when you go from the terabyte to petabyte to exabyte scale. And again, users need to get away from keeping data on their laptops and then be comfortable with putting data on cloud. So this also allows them to work with all those massive corpuses of public data, which are already on cloud, and that's what Cloud Bank is going to enable. CyVerse uses this iRods container storage interface driver, which we've implemented underneath our Kubernetes which mounts our data store as a drive in our container. So users can access all of their data in a container. So last, our novice user, how do we help them? So a recent survey of NSF life science PIs found that researchers are not lacking for access to computation or data storage. Really what their greatest unmet need is a lack of skilled scientists in the workforce that can leverage the resources we have. So it's our job to train them. And so we train people. We run workshops. We've been running these for years. Once COVID hit, we went fully online, and because our platform was already on the cloud, we were able to take our students and just move them remotely right away. Currently, we teach a couple of container series on building your own containers, and then foundational open science skills, learning how to do reproducible research. So thanks for your time. If you'd like to learn more, you can go to cyverse.org and find out more about us.
Thank you, Tyson. That was really exciting stuff. All right, next up, we have Jeff Albert, Senior Unix System Administrator for the Research Computing Wing of the University of Victoria.
Hi, everybody. I'm going to hope that you can hear me and see my slides, but please yell if you can. So yeah, I want to speak to you today about ComputeCanada's research community clouds. Many of you are probably familiar with the terms private cloud, a cloud that's only available to people inside an organization, or public cloud, available to anyone who can pay for it. The ComputeCanada model is more of a community cloud approach, and the community in question, of course, is Canadian researchers. So yes, I am Jeff Albert. I'm a Senior Advanced Research Computing Systems Administrator with the University of Victoria. And because the University of Victoria is part of the ComputeCanada Federation and participates in hosting one of the large cloud sites here, the Arbutus Cloud, I also serve as Cloud Architect on the ComputeCanada Cloud National Team. So ComputeCanada's model is to provide digital research infrastructure for Canadian researchers in a national way. We provide a national infrastructure model that co-locates cloud and HPC sites across the country. In particular for cloud, we've got the large Arbutus site here at UVic. There's also smaller cloud sites that are co-located with the other supercomputers across the country that are generally meant more for portal access to the data sets that are being created at those supercomputer sites. So Arbutus is the large capacity cloud, and it offers vGPUs, block object and shared file system storage, and is generally an infrastructure as a service cloud foundation for Canadian researchers. All those sites across the country are connected to the Canadian Canary NREN, which provides 100 gigabit connectivity between the sites. So this is quite a well-built foundation on which to operate infrastructure as a service workloads. The model also includes flexible allocations. So the idea here is that every year, researchers can compete for a major allocation cycle, and all Canadian faculty are eligible to participate. But in the interim period between those allocations, all Canadian faculty are eligible for smaller rapid access allocations, which they can essentially take up at any time and which can graduate into a competition for a major allocation at any of the annual cycles. We also facilitate a collaborative national team support model. So in addition to all the institutions participating in providing the physical infrastructure, the data center space, the networks, we also collaborate together on providing support across the country. For Canadians, of course, it's important that that support is bilingual. So we have team members across the country who are versed in both languages. We also have team members who are versed in specific fields, scientific fields, and specific technologies. And so being able to draw on those national resources that aren't fragmented to individual sites or institutions or regions provides a strong foundation of support for the researcher community. In particular, the community cloud approach is of interest, I suspect, to this group, probably because of the way that it differs from the commercial cloud approach. In particular, in the ComputeCanada model, cloud infrastructure is directly capitalized. So this is funded cooperatively by federal, provincial institution partners on a regular basis. We proceed through the process of identifying needs and then building out equipment that serves those needs. That's not something that individual researchers need to produce granting directly into. That's something that's funded as a national objective and that all of the, as I say, sites, regions, and federal partners contribute to. And because of that, our allocations to researchers are quotas, not meters. So when you get an allocation, whether that's a rapid access allocation or a larger rack allocation, you essentially get reserved access to those resources. And although you may not use all of them, and we do over provision to maximize utilization, essentially you're not penalized and you don't pay a cost for the actual usage. You just get access to the total resources that you feel you will need. The bonus here in particular is that this encourages experimentation and innovation, and it resists the sort of chilling effect that can sometimes be the result of metered billing, particularly when you're trying to build something new and you don't yet know what tools you're going to need to use or how well those will scale. The sight of the cost number climbing rapidly towards your budget ceiling can be a real chill to innovation. So providing a quoted rather than metered approach is part of why we or how we achieve that flexibility for researchers. And similarly, that support cost is also federated across regions and funded nationally so that it's available to everyone at every institution in every field, whether or not those teams already have a strong background in advanced research computing, whether or not they're already aware or experienced with cloud, that support is available to them. And by and large, this has been a very successful model for Canadian research. One of the big successes on the Arbutus Cloud has been our Atlas Tier 2 site, which operated for close to 6 years as a bare infrastructure as a service model. So it was the 5th most reliable site in the world operating on that system. Most Atlas Tier 2 sites were operating on bare metal at that time. And in the intervening period, we undertook a collaboration between UVic and CERN to develop a Kubernetes-based Tier 2 site, which has been in active production for almost 2 years now, maintaining that same top-grade availability. Interestingly, the GenApp project was one that is researcher-led. So it's a collaborative portal for genomics research. It's essentially a platform as a service built on top of Arbutus's infrastructure as a service, but it's part of a researcher-led initiative. And so that's something where individual projects from multiple institutions can log in and get access to that portal and work on those data sets together. This last year, Arbutus hosted the HackSeq RNA hackathon, high risk, high reward research projects on COVID-19. The neat thing about this was it was sort of subdividing an access allocation for really agile project scaffolding. So it was literally just a whole bunch of people with great ideas who came in under a single rapid access allocation. We carved it up, gave everybody a small number of VMs, and they tried out to see what would work. Numerous of those projects actually graduated to their own fully fledged rapid access allocations, and some of them are moving towards longer major allocations based on the outcome of that work. And finally, New Horizons. This one is just one that I find really fascinating. So this is the probe that NASA sent to and then past Pluto a few years ago. The navigation process for identifying a path through the asteroid belt and past all the navigational hazards between here and Pluto, and then on to the ultimate Thule item that it intercepted after Pluto. Very complex, and of course not something you can do in real time. So the team used Arbutus to do big data indexing on a catalog of photographed navigational hazards that they were aware of, and then provided a collaborative data portal to an international collaborative navigation team, and ultimately did design a successful navigation plot, which did bring that probe successfully all the way to Pluto and past it. So very, very successful project implementations on that community cloud. In the spirit of lightning talk, I have talked really fast. I think I've gotten through everything, but thank you very much for your time.
Thank you, Jeff. That was a really cool amount of information fit into a lightning talk. And thank you for the links for us to learn more. So